Hi everyone. Now we are going to discuss about stability of carbanion that is influenced by different factors. We uploaded regarding carbanion 3 videos. In the last video we did some factors that are influenced by stability of carbanion. Now in this video we are going to do some more factors that are influenced by stability of carbanion. Let's start now. Here we'll take an example. There is CF3 carbon carrying negative charge and CCl3 carbon carrying negative charge. You know, CHF3 fluoroform, CHCl3 chloroform, right? That is haloforms. Here the carbon is bonded with 3 fluorine atoms, okay, and here carrying negative charge, and this one the carbon is bonded with 3 chlorine atoms, right, and it carrying negative charge, okay. Now, so generally of these two, which is more stable? Generally students or responses, sir, CF3 is more stable. The answer for that, the reason they are saying is, so fluorine is more electronegative, withdrawing power is more, so that's why it is more stable by withdrawing electrons from the carbanion, right? But that is not correct. So what is the exact reason that is here? So in case of fluorine, D atomic orbitals are absent, but in case of chlorine, D orbitals are present. Then here the main thing is operated here, D orbital resonance. What is that? Here, so the chlorine having D orbitals, no, D orbitals are dumbbell shaped, that is 4 lobes are a double dumbbell shape, 4 lobes are present, right? So this is the double dumbbell shape D orbitals, right? Okay, you have to represent like this. Yeah. So now the negative charge accumulated over the carbon atom is delocalized into d orbitals. There is dispersal into d orbitals. This type of dispersal of negative charge on the carbon into the vacant d atomic orbitals is called d orbital resonance. The d orbital resonance is not be observed in CF3. Why? Because in fluorine there is no vacant d orbitals. Fluorine atomic number is 9. It have 1s2, 2s2, 2p5 configuration. So second cell is the valency cell. In the second cell, d orbitals, 2d orbital is not existed. D orbital is first time existed in the third main shell, that is 3d is there. So that's why vacant d orbitals are not present in the fluorine. Okay, so that's why now the reason is, so here d orbital resonance, because of that CCl3 minus is more stable than CF3 minus. The reason is, what is that? D orbital resonance. So what is d orbital resonance? That is simple reading I am giving to you to easily understand the concept, simple sentences, right? You just follow that. That is here the negative charge on carbon atom, that is on carbanion, is dispersed into the vacant d atomic orbitals, right? So this is called dispersal of charge. Negative charge is dispersed into the vacant d orbitals, means charge density, negative charge density over the carbon is decreases. If negative charge density decreases, stability of carbanion increases. Yeah, that is the case. That is, you know, negative charge density decreases, then stability of carbanion increases. Is it clear? Okay, so this point you have to keep in our mind, and this is the main reason. Okay, is it clear? Next, move to next another example. Here the compound is given to you like this. It having a phenyl ring. Okay, so there is a double bond, single bond, double bond, single bond, double bond, and here one phenyl ring. Okay, and here also one phenyl ring. So 3 phenyl rings are there, and this carbon carrying negative charge. Okay, then another compound is here. This is hydrogen atom, and here phenyl ring is present, phenyl ring is there, okay, and here also phenyl ring is present, okay, yeah. Now of these two molecules, compounds, carbanions, which is more stable, right? So generally the student answer is here 3 phenyl rings are there, so they are all giving more stability to the carbanion. No, that is wrong. Then what is the thing that is happening here is steric hindrance. So I will give complete explanation regarding this one. Yeah, follow here. So in this case, the carbon carrying negative charge, it is bonded with 3 phenyl rings. So phenyl rings are stable. Why? Because of what is the thing that is happening here? That is delocalization. That is called delocalization. That is called delocalization of pi bond electrons along the length of the carbon chain. That is called resonance. Okay. And also here aromaticity is there, that is 4n plus 2 pi electrons, okay. So that's why the 3 phenyl rings are more stable, highly stable due to that is resonance and aromaticity, right. So that is the 3 phenyl rings, highly stable due to resonance and also aromaticity, right. Because of that, the electron density on the phenyl rings is more, high electron density is concentrated, okay. So the electron density concentrated more here, okay, that will repulse the negative charge on carbon atom, right. That is the high negative electron density on 3 phenyl rings, repel the negative charge on carbon atoms, negative charge on carbanion, okay, negative charge on carbanion, okay. So because of that, repulsions are take place. So because of repulsions, okay, it is charge dispersal is not take place here. They repulse with each other, right? Okay. So high electron, that is the similar poles are repulsed right here. Negative charge, high electron density is there here, negative charge, and here also negative charge, repulsions are take place. Okay. So that's why it is stability, that is delocalization of dispersal of charge is not much take place. That's why it is less stable. That is okay. And that too, one more reason is here. The 3 phenyl rings are accumulated here. They occupy the more space. So that's why crowdiness is there. This is called steric hindrance. Okay. So that they are all occupying this. So dispersal of charge is not much take place. So this called as crowdiness increases. So that's why this is called steric hindrance. Bulkiness of the 3 phenyl groups or crowdiness of the 3 phenyl groups. Because of that, the dispersal of charge is not much take place. That is called what? Steric hindrance. The next one is what? Steric hindrance. Steric hindrance of 3 phenyl groups. Okay. So because of that, what happened? The dispersal of charge is not much take place. Dispersal of charge not much take place. Not much takes place. Okay. Not much take place. So that's why it is less stable. Is it clear? Right. Then what about here? So in this case, here also the 2 phenyl rings are there. That is, the number of rings are less. So that's why here also repulsions are there, electron density. So here also that is electron density is more. Here also that is resonance is take place and aromaticity is there, 4n plus 2 pi electrons. So here electron density repulsions are there, but the repulsions are less compared to this one. Okay, so that's why here, so the repulsion strength is less. So that's why dispersal of charge is somewhat more. So that's why it is somewhat more stable than this one, right? Okay. So here the thing is that is the repulsion strength is less. Repulsions are less, and that too steric hindrance, because here 3 groups steric hindrance is more, 2 groups steric hindrance is less, right? There is steric hindrance is also less. Steric hindrance is less. So because of these two less, steric hindrance is less and repulsions are less. Okay, because of that, the stability of this molecule is more, right? So it is more stable. It is more stable. Somewhat more stable. Somewhat more. There is dispersal of charge is somewhat takes place compared to here. It is more. Okay, so that's why charge dispersal is take place. So that's why here charge dispersal because of less steric hindrance, charge dispersal is take place somewhat more. Here very less. So that's why it is somewhat more. That's why it is more stable, and this is less stable. So this is less stable and this is more stable. So this one, this is triphenyl methane carbanion and this is diphenyl methane carbanion. Which is more stable is this one is more stable because it is repulsions are less, steric hindrance is less. So that's why charge dispersal is more here. So that is what the thing is happening. Charge dispersal is take place. Charge dispersal is take place. Charge dispersal is take place. Right. So that is charge dispersal. Charge dispersal is take place. Charge dispersal is somewhat more here. Got it? Charge dispersal is more here. So that's why it is somewhat more stable. Is it clear? Right. Okay. Yeah. Got it? These two. Copy it. Yeah. Take a screenshot. All of you fine? The following. Yeah, next one. Next factor is, so here what is the factor here, my dear students? First factor we did, that is D-orbital resonance. Second factor is here in these molecules, that is steric hindrance. Steric hindrance. Steric hindrance. It will decide the stability of carbanion. Is it clear? Right. Next, the third one. Now we will go ahead. We will go ahead to discuss about the third one. Right. Here in this case, we will take a different example. Okay. Yeah. So in this molecule, it is we make it. There is negative charge is there. Here double bonds are there. Okay. And this is one previous year question. So of these two, which molecule is more stable? Yeah. So this is cyclopentadienyl anion. This is cyclopropenyl anion. Right, which is more stable. So how many carbons are there? 5 carbons. So cyclical polycyclic compound, pentadienyl. So double bond is repeated 2 times. Dienyl, cyclopentadienyl anion. This is cyclopropenyl. E means double bond, right? Okay, yeah. Now in this case, which is more stable here? So how many pi electrons are there here? There is 2 covalent bonds, and these electrons are participate in resonance stabilization. These d electrons are delocalized, right? They are not localized, so they participate. They make a bond here, pi bond. Then these are they migrate over here. That is happening, right? That means these 2 electrons involved in the bond formation, delocalization. That's why these are also pi electrons, right? So how many pi electrons are there here? So there is 2, 3, 4, 5, 6. So 6 pi electrons are there. So 6 pi electrons are there means they obey. There is 4n plus 2 pi electrons rule. So if n value will get to 1, then we will get there is 6 pi electrons. Okay. So that's why it is an aromatic compound. It is an aromatic compound, right? It is aromatic, yeah. Then, in case of aromatic compound, charge dispersal is take place. So that's why the negative charge density on the carbon atom is dispersed along the length of the carbon chain. So that's why it gives more stability, right? So negative charge density is less, stability increases more, right? Yeah. Then what about here? In this case here, these electrons are participating in delocalization. Then it make a bond and these are migrated here. So that's why totally here, how many pi electrons are there? 4 pi electrons are present. 4 pi electrons are present means it is a it obey there is a 4n pi electrons rule. There is we will get here n value is 1, so 4 into 1 4 pi electrons. So there is anti-aromatic, right? It is anti-aromatic. It is anti-aromatic. So that's why it is anti-aromatic. Then what I mean? This charge delocalization, charge density decreases not there, right? So generally dispersal of charge is happening in aromatic compounds, you know, right? Resonances take place. So that's why now. So because of aromaticity, this compound is more stable than this. Got it? Here, what is the factor here? There is aromaticity. Aromaticity also responsible for stability of carbanion. Is it clear? Right? Okay. Next. Now we'll move next another example. Now, in this case, I am going to give the compounds. So still now we did about that is three. One is D-orbital resonance, and the second one is steric hindrance, and the third one is aromaticity, aromatic character. Okay, right. Then that means the molecule which having aromatic character, there is going to most stable. So that's why there is more stable carbanion than the molecule having anti-aromatic, right? Well, next example we will do now here. So in this case, I am taking now CH2 Cn and this molecule, and another molecule is C. There is taken Cn taken thrice. So here negative charge is there, and here also negative charge is there. So this is a previous year question, or a favorite question, this one. So which is more stable here? So this is here the carbon, this carbon carrying negative charge, and two hydrogens are there here. Okay, and this side is one with carbon, and this carbon having nitrogen with nitrogen. Three bonds are present, right? Okay. So then what happened here? So this negative charge, what is there here? Conjugation is there. That is double bond, single bond, or negative charge. Conjugation is there, means resonance is take place. There is dispersal of charge, delocalization of pi bond electrons, or delocalization of low pair of electrons, or this negative charge here. These two electrons might go over here, they make a bond here, and these pi bond electrons are over here. Then we will get there is going to stable charge, negative charge density dispersal, right? So then dispersal of charge is there. So negative charge density decreases because of delocalization, dispersal of charge. So that's why this is stable. Then what about here? So in this case, so to this carbon carrying negative charge, okay, and is bonding with the three cyanides, right? So this is three are bonded, right? 1, 2, 3. So here cyanide ion, okay, and here also cyanide ion, and here also cyanide ion, right? Okay. Now, so in this case, this negative charge is dispersed from here to here, then is moved from here to here. Then this negative charge is taken by this one also. Yeah, that means here the dispersal of charge is more in this case because of three cyanide groups are there, right? So that's why more the dispersal of charge, then the negative charge density decreases more and more. Negative charge density decreases means stability of the carbon increases, right? So charge dispersal is more here. So charge dispersal is more here. Charge dispersal is more here. If charge dispersal is more, okay, negative charge dispersal is more. Got it? If negative charge dispersal is more, okay, then what happens here? There is a stability of carbanion increases. It is more increases, stability of carbanion is more increases, right? But here also there, but that much dispersal of charge is not take place here. Okay, so that is called, we have to call it as what? There is resonance. So here resonance is there, here also resonance is there, but resonance is here a minimum, but here resonance is maximum. Resonance is maximum is happening. Okay, so resonance is maximum take place here. There is less charge dispersal. So here two hydrogens are there, but all our cyanide groups are there. So there is less charge dispersal. There is less charge dispersal means, so charge density is not that much decreases. Okay, less charge dispersal. So that's why it is less stable. This less stable, and this is more stable. This is more stable. Is it clear? Right? It is more stable. Got it? Yeah. So that's why this is more stable, right? Fine. Yeah. Copy it fast. Next one. Take a screenshot. Next one. Another example. So here the factor we did is resonance. Okay. Now we move to another example. This carrying negative charge. Okay. So there is single bond, double bond. Okay. Then here single bond, double bond. Next one. It is carrying negative charge, and here double bond, here double bond. Next, we take it here. This compound negative charge, here bond. Right. Yeah. So of this, which is more stable here? Look here. In this case, here, this negative charge is dispersed here. Okay, double bond, single bond, negative charge, and this is dispersed over here. It moves delocalized, and this is dispersed here, right? So this is what? This is linear conjugation, right? Linear conjugation. And in this case, what happened? So this negative charge is there. So this negative charge is dispersed from here to here. Okay, this is migrated over here, and this may be dispersed over here. Then this is migrated over here, right? So this is called what? Cross conjugation. Here, linear conjugation. Linear conjugation, and here a cross conjugation. So conjugation is from this side and from this side. This continuous linear conjugation. Okay. So this is called what? Cross conjugation. Cross conjugation. And in this case, here, what is that? Here, this negative charge, it is migrated, dispersed from here to here. Okay. And then from it is dispersed from here to here. Then is this from here to here. This is called what? Cyclic conjugation, right? This is what? Cyclic conjugation. Okay. So all have conjugation is there. Okay. Then conjugation is different types. What is that? Linear conjugation, cyclic conjugation, and cross conjugation. If the molecules carrying this type of three conjugation, among this, which is the most stability here? Look here, in this case here, cyclic conjugation, and here this is linear conjugation, right? So in this case, continuously it is migrated right here, okay? So cyclic conjugation is it is migrated along the length of the carbon chain, and it is stopped here. So that's why here cyclic conjugation is more stable. Next one is linear conjugation. Next one is cross conjugation. Cross conjugation. So this is the factor. Is it clear? Okay. Yeah. So I think I enjoyed this video. Okay. So thanks for watching my video. Like it, subscribe it, and share to your friends. Okay. Fine.